So far, I've been telling you stories about what people tell us the galaxy is made of. I've told you how much the mass of the disk is and how much the mass of the halo is. And most of these, other than the gas discovered by Chandra, were estimates based on basically star counts. We count the stars, and therefore there's some uncertainty because remember, the number of stars in the Milky Way is uncertain to almost a factor of 2, depending on what the prevalence of brown dwarfs is. But brown dwarfs don't comprise a significant fraction of the mass of the stars, since they may be numerous, but they're not very massive. So we have these estimates, but it would be good to make an independent comparison of a direct measurement of the mass of the galaxy. How do you weigh a galaxy? Well, by now we know how to weigh anything. You just need something to orbit it. If only we had something orbiting the Milky Way. Oh yeah, we do. We orbit the Milky Way. So all we need is the orbital parameters of the sun, and you'd think that's an easy problem. In fact, it's a lot trickier than you think. The distance of the sun from the center of the galaxy that I quoted as 8 kiloparsecs is one of the least precisely known numbers in astronomy. In fact, it's somewhere between 7.5 and 8.5 kiloparsecs, so there's a 12% uncertainty or 6% uncertainty in this distance. It is a difficult measurement to make. Likewise, the speed with which the sun moves as it orbits the galaxy. You'd think that's an easy thing to measure, but it's not easy because remember, all around us are stars that are moving in their own peculiar motion, and along with that, with some average motion that is essentially ours. And so getting a correct value for the speed with which the sun moves around the Milky Way is also not trivial. I'm going to use the established values. There are some uncertainties, but they're not going to affect what we're going to do significantly. And if you compute 2 pi r divided by v, you find that the sun orbits the Milky Way once every 230 million years, which means that in the 5 billion year history of the sun, we've gone around the Milky Way about 20 or 25 times. So the sun has sampled all kinds of places in space in the course of its history. And now we're back to Newton. We know exactly how to do this. We have an object that is orbiting. We know its period. We know it's the radius of its orbit. The sun's orbit is roughly circular. And so we can make a calculation. The easiest way we know how to do that is to do our favorite scaling compared to the Earth's orbit around the sun. The mass that the sun is orbiting is related to the solar mass by the ratio of the periods to the -2, ratio of the radii cubed. Plug in all the numbers and you find 88 billion solar masses is what the sun is orbiting. Now, that is a little bit higher than the numbers I quoted for the galaxy, but remember that, and I'm going to make a slight fudge here, but I'll explain it. If the galaxy were a spherically symmetric object, then the sun would be orbiting precisely that fraction of the galaxy that is within its orbit. The galaxy being spherically symmetric, everything outside the sun's orbit would have no impact on our orbit. Everything inside it could equivalently be placed at the center. We talked about that when we did Newtonian gravity. Now, the galaxy is not spherically symmetric. It's distinctly a disk. This adds a small change to the calculation. It is still true that everything outside the sun's orbit has 0 impact on our orbital acceleration. However, there's a small geometric factor, a factor of order 1, that is associated to the fact that the mass inside our orbit is mostly located in a disk, were that the case. But our estimate is still good, and we found that what the sun is orbiting is slightly more than the total mass that we had for the entire Milky Way galaxy. That's interesting. Typically, so we want to figure out what it is we've missed. Are there a lot more brown dwarfs or whatever than we thought? To study this, the way this investigation is done is typically, instead of using this nice scaling relation, which I confess is my favorite way to do it, the way we usually do it is we write that an object that is orbiting at a radius r with speed v has a centripetal acceleration, which we computed in the second week of v squared over r, and that is given by the gravitational acceleration about whatever it's orbiting. So we would put m of r over here, where m of r is the mass inside the circle of radius r in which this object orbits, and I should say r squared. And now that I've written the correct formula, I can cancel this r, and we see that v squared is g m of r over r. This is exactly 1/2 the escape velocity, if you remember that calculation. And so the way this is usually written is that v squared gives you, if you measure the speed with which something is orbiting and the radius from the center at which it is orbiting, you can figure out the mass enclosed within its orbit. Okay, the study of galactic rotation curves is something extremely interesting. What is it that we expect and what is it that we find? So here's what we expect. In red here, I've drawn two red curves. The first is the measured stellar density. And you see that it's an exponential density in the disk. The stellar population is densest in the center of the disk and then smoothly falls off. You see that by the time you get to the sun, it has fallen to about 1/6 of its density at the center, and it continues to fall off rapidly. This, if you compute how much mass is within a disk with this density, you find this red curve. We're going to make an approximation because it allows me to do a calculation. The approximation I'm going to do is I'm going to replace this crazy disk by a uniform disk with a uniform mass distribution. So I'm going to imagine that I have a disk of some thickness, say t. This is, again, assumed uniform. We can make it 1 kiloparsec or something like that. And some density rho in kilo per meter cubed, or 10 billion solar masses per kiloparsec cubed would be the more standard units to be using here. And so I have a density and I have a thickness, and I'm going to give my disk some radius r. And the way I've fixed all of these parameters is I've fixed t and rho so that the stellar density out where the sun is at 8 kiloparsecs agrees with the actual stellar density. And then I fixed the radius so that the total mass of this uniform blue disk is the same as the total mass of the stellar disk. So what is m of r in this case? Well, in this case, m of r is pretty easy to write. M of r is rho times the volume of all of the stars. I'm wanting the mass of all of the stars enclosed in a circle of radius r. Those stars enclosed in a circle of radius r form a cylinder. I'm great at drawing cylinders. A cylinder of radius r and height t. So its volume is pi r squared times t. And I will sometimes fall into using lowercase r for the radius because that's the way it's done in the field. So this is m of r. Our calculation said that v of r should be, if this is what you are orbiting, v of r should be, let me make a correction to this in a minute, v of r should be the root of g m of r over r. Now, what is this going to give me? Well, m of r is rho times the area of a disk of radius r times t, as long as r is less than r0, which is the radius of my disk. As long as you're orbiting inside what I called the uniform disk, then the farther you are, the more you are orbiting. Of course, if r is bigger than r0, then the mass inside your orbit is simply m, or rho times pi r0 squared t. You're not orbiting any more by orbiting farther outside in the vacuum if you're orbiting at distances out here. And so, what is v of r? Well, I can do this calculation, and if r is less than r0, there's a whole bunch of constants that I'm not going to worry about, but m goes like r squared. I'm dividing by r, so v is going to go like, well, okay, the root of rho pi t g times r. It's going to grow like the square root of r. So the farther you are from the middle, the faster you're orbiting by this square root of r. The reason, remember, in the solar system, the farther you are from the sun, the slower you orbit. That's because we all orbit the same mass. We're all orbiting the sun. Here, the farther you're orbiting, the more mass you're orbiting. Therefore, your orbital speed will increase. But once you hit r0, then, of course, the result is that m no longer depends on r. We'll call all of this m. And so now it's just root of gm over r. The only r dependence is in the denominator. So we expect something that grows like the square root of r and then decreases like 1 over the square root of r to be the plot of v as a function of r, which is what I'm about to plot. But I wanted you to show you that this is not some mysticism. We can actually do the calculation. And so here is the prediction. Indeed, the blue line does what we expected. It grows like the square root of r. This is the plot of a square root. And then once you are outside the disk, you've reached the maximum speed. You're orbiting as much as you're ever going to orbit. Farther out, you're orbiting the same thing but at a larger radius. So your orbital velocity decreases. Notice that the mass curve, the m of r curve for the blue curve is not a bad approximation, considering the simple assumptions I made. To the red curve, they're different. Inside the sun's radius, they certainly agree almost exactly past the sun's radius because most of the mass is within that. So the red curve differs, the prediction for v of r differs closer in than the sun, but past the sun's radius, they pretty much agree. Okay. This is not yet a real galaxy. To have a real galaxy, you have to take into account that there's also a bulge in the middle. So how do we add a bulge in the middle? Well, just to be very simple, I have added in this picture, this is the red graph we had before, I have added a bulge which is a uniform homogeneous sphere of radius 3, whose mass is adjusted, 3 kiloparsecs, whose mass is adjusted to be exactly the mass I predicted for the galactic bulge. And so up to radius 3, there's this extra increase because you're now orbiting more and more in the bulge. And then past the outside of the bulge, the total mass orbited gets a constant contribution for the mass. And so the total mass you're orbiting is now this black graph that I've drawn over here. And from this, I can again reproduce a graph of v of r. I've broken it up into contributions. This would be your orbital velocity if you only orbited the bulge. If you want the fact that this increases in a straight line, it has to do with the fact that the mass you're orbiting inside a radius r, as long as you're inside the bulge, the mass you're orbiting is m of r for r inside the bulge. M of r is rho of the bulge, if you're just talking about the bulge, times the volume of a sphere of radius r, which is r cubed. And so m of r over r, which is what goes into v, goes like lots of constants times r squared, and v squared going like r squared means v goes like r. In a homogeneous a ball of homogeneous density, your radial velocity increases linearly. Okay, and not your radial, your orbital velocity increases linearly. The outside has to orbit faster. This is great because this also means that v of r proportional to r is what would happen if you just took that ball and rotated it rigidly. So a homogeneous ball rotating, orbiting itself under the force of gravity, rotates like a rigid ball, at least in the plane of the orbit. In the plane of the equator, a straight line drawn from the origin to the equator will continue to stay a straight line. Everybody orbits. The period of everybody on the equator is the same. That's an interesting observation. It turns out that this does describe in real galaxies the behavior at very small radii. And then we have the red curve, which is the same curve we had before. Adding them together, we get this black curve. The sharp corner here is an artifact of the sharp corner here of my approximate model of the bulge, but I wasn't about to insert bars. It gets too complicated. So I wanted to see that we could make a reasonable prediction as to what the velocity curve should look like. We already know that we're falling short because I inserted the measured masses. So this gives the sun a velocity of about 180 kilometers per second, whereas the measured value is 230 kilometers per second. But we knew we had a short falling in the mass there. The big question is going to be what happens out here, outside the solar radius. And we have measurements. Here are the measurements. So remember, 8 kiloparsecs is where the sun is. So this is the solar radius. The sun is here measured at about 225 kilometers per second. I told you that measurement is subject to corrections. And here, as a function of r, is the observed rotation speed. And what it is that's being measured are carbon monoxide clouds and molecular H hydrogen clouds and 21 centimeter emission from atomic hydrogen. Various things have been used to make this measurement. And what we see is indeed the steep increase, linear with R, near R equals 0. Then the decline when you leave the dense region. This structure is associated with the galactic bulge, and modeling it more precisely, we get out to the sun and we're a little underestimating. And then what goes on here is a disaster. The VFR graph starts decreasing as we predicted. Remember, it was supposed to start declining because you're outside essentially the entire mass of the disk. And it's not declining. It's staying constant. So not only are we missing some mass inside the sun's orbit, but the farther and farther out we get, the more and more mass we're missing, because what we're finding is that m of r over r is a constant. The mass enclosed within radius r is growing linearly with r. And where it stops growing linearly with r, this graph is not going to show us. It becomes tricky to measure it here. We'll have more luck actually measuring this with other galaxies. So the resolution of this problem, we'll wait until we see whether it's some crazy quirk of the Milky Way and of us being stuck in a disk and not measuring very well, or actually a more general thing. But I wanted to bring it up, and also we had to do a calculation.